All right. Good afternoon or good morning, wherever you're listening to us from. And welcome to TME Presents, Restoring a Missouri River Basin Levee. You've read the article, now learn the rest of the story. I'm Daniel Wheatley, Associate Editor for the Military Engineer, and it's my pleasure to welcome you here today. Before we get started though, I'd like to go over a few items so you know how to best participate in today's event. All the attendees are in a listen-only mode for the presentation. You can use the chat pane to chat with your fellow attendees. Let's try that now. Everybody type in where you're listening from today. For me, it is a snowy Virginia country that I'm in. You can submit questions for the presenters at any time by using the questions pane of the control panel. We're going to collect these and address as many as we can during the Q&A session at the end of the presentation. Please also submit any technical issues you may be encountering here as well. Originally published in the July-August 2021 issue of TME, Restoring a Missouri River Basin Levee covered a project to repair and close a federally managed levee system in northwestern Missouri after catastrophic flooding due to a bomb cyclone in March of 2019 overwhelmed the downstream Missouri River flood control system. The approach utilized mechanical sand removal and leveraged local subcontractors to expedite the project's completion and also increase the final resiliency of the surrounding community. And with that, I'd like to introduce the authors of the article and today's speakers. Dwight Gemar, PE, is Vice President and Principal Project Manager with Weston Solutions, where he leads and manages rapid response and large-based closure remediation programs, including closure of major breaches within the Missouri River levee system. Adam Brown, PE, is Deputy Director of Engineering and Principal Project Engineer for Geotechnical Design at Weston Solutions. He was an initial responder to the Missouri River levee system repair and led incidental engineering design tasks involving borrow planning and monitoring and planning for breach closure, geometry, and hydraulics. And our third speaker, Natalie Harkins, PE, is practice leader of civil and geotechnical engineers and project engineer, also with Weston Solutions. She performed both field and home office support of the Missouri River levee system repair and led engineering and construction engineering tasks for both major breach closures and borrow infrastructure planning. With that, I'll turn it over to our featured speakers.
Thank you, Daniel. This is Dwight Gemar. It's a pleasure to be with you for this webinar. I served as project manager on site during the work that we'll be describing during this presentation. Both Adam and Natalie were also on site providing engineering support during the flood fighting stage of this work. For some background, in March of 2019, the Midwest, upper Midwest experienced a bomb cyclone weather event, which dropped heavy snow in the area. And this was followed by heavy rains, which melted the snow and while the ground was still frozen and created large runoff, as you can imagine, into the tributaries of the Missouri River. This in turn overtopped the downstream levees across the multi-state area, resulting in 50 breach locations within the Army Corps of Engineers Omaha district footprint, and resulted in massive flooding in Nebraska, Iowa, Missouri, and Kansas, which of course caused major damage to roadways and outages, as well as bridges and rail lines. The photograph on the right shows one of the large breaches in the levee unit 550 location, which is going to be the subject of our presentation this morning. For background, the levee unit 550 is shown on this slide. It's, as Daniel mentioned, it's in the northwestern corner of Missouri. It's 32 miles long. It's shown by this dark black line on this figure, and protects a roughly 40,000 acres. The levee unit begins in the ties into the high ground east of Interstate 29 at the northern portion of the figure, and proceeds along the Nishnabotna River and High Creek to the north, and then follows the Missouri River further south, and then eventually turns northeast, and tying back to high ground in the east of the interstate. The flooding caused two large inlet breaches. The northernmost breach was labeled Breach A, and was where both the Nishnabotna River and the Missouri River were flowing through. About 5 miles downstream, another inlet breach occurred, labeled Breach B, which additional water flowing from the Missouri River entered the breach. As the floodwaters proceeded to inundate the area, which encompassed pretty much the entire area between the levee and Interstate 29, the floodwaters also damaged and basically cut off Highway 136, which is a major artery between Missouri and Nebraska. And further south, the floodwaters caused 5 outlet breaches where the waters then returned to the main channel of the Missouri River. These outlet breaches were labeled as outlet breaches C through G. And in addition, throughout the levee system, there was numerous areas where major erosion of the levee cross-section occurred, as well as slope and seepage berm damage. A couple other things to note on this figure is the location of 2 inland areas that were potential borrow sources, which are shown in kind of an orange color. One was located adjacent to Breach A, which were sand deposits from the 2019 flooding event. Another potential area of borrow for non-cohesive was about 1 mile north of the B breach, which actually were sand deposits from a 2011 flood event and breach. Also to note, for future reference, cohesion areas were located in the areas up in the north toward High Creek, and then further south at Rock Creek. So in June of 2019, there were still massive flooding occurring. The water levels were still well above flood stage in the Missouri River. And this was due to heavy rains that continued through that spring. Also, the upstream dam at Gavins Point in South Dakota was having some heavy releases, and so that contributed to the high levels of flooding in this area, even into the month of June. In that month, the Corps of Engineers awarded a contract to Weston Solutions through a contract geared toward rapid response for repairs of infrastructure. And this was managed again through the Omaha district of the Corps of Engineers. The initial objective of that contract was to close the inlet breaches to stop the flooding, as well as to restore the levee height in those areas to a 25-year flood protection elevation. Subsequent work that was awarded under that contract involved a closure of the outlet breaches, repair of the critical infrastructure loss cross-section, and restoring the levee to pre-flood or as-built conditions. as well as repairing slope and seepage berm damage, and also restoring the levee crest surfacing, and to, in some cases, repair drainage structures. In June of 2019, the site conditions were still quite challenged due to the active flooding. Roads accessing the levees were flooded and damaged. The inland borrow areas, which were targeted for non-cohesive sand deposits, were underwater. Therefore, the quantities of available fill were unknown. The Corps of Engineers did offer the potential for a couple of borrow areas within the channel of the Missouri River itself. However, there were other levee systems further upstream that were already under repair, and river dredges were unavailable. Also, the high river levels due to the continued flooding were a challenge and probably would have precluded dredging in the river. The breach A especially had a very high volumetric flow rate, measured at over 15,000 CFM, which was going to be a challenge, as Adam and Natalie will describe. And the fill volumes were quite large, estimated by the Corps of Engineers at a roughly 850,000 cubic yards. So again, these were some of the site conditions that proved to be a challenge as we mobilized to the site in June of 2019. At this point, I'll turn it over to Adam Brown, and he'll describe a little bit more detail some of the technical aspects of the work involved in getting the initial closure completed.
That's right. Thanks, Dwight. So the task was simple: fill the breach. Our first step was to get closure restored and stop the flow of water through breach A. This was the largest contributor to floodwaters in the sectional levee. Once we got that established, we could build a landside berm and buttress the closure berm and really start filling the large scour and riverside losses. Once we were high and dry and had our base set with phase 2, then we could start building our sand core and armoring. We did have recent bathymetry that was shot right after the failure occurred, that was provided as part of the early phase before we mobilized to the site. So here's that same breach. This is a breach in cross section. Note there is a scour hole located to the bottom left of the cross section. There was an additional scour hole deeper than this, about 30 feet deeper, that was further south on the levee section. Knowing our closure berm could be anywhere inside this section, we plan to align it in that blue area to the right, as suggested by USACE in their planning documents. This was the land side. It was the shallowest, and it wasn't the straightest distance to closure, but it minimized the quantity of soil needed. And that's kind of the beginning of the story of how our first contingency plan was about to take shape. But first, we'll talk a little backstory. So here's one of the many tick maps we produced during the project. The ticks show the value in feet elevation between two surfaces, and it shows as red when the 2011 survey was lower than the existing grade, and the blue means that the existing grade was higher than that pre-flood survey. This blue reflected a deposit of material that we could plan to use to fill the berm. To get this survey, we couldn't just fly the area. This is about a square mile area, which would be really nice to be able to fly, but we can't do that when most of our material is below water. Also, the water was fairly shallow, so actually doing bathymetry was pretty impractical. So we captured most of this using manual surveying on foot, and then shallow depth manual surveying with surveyors stationed on airboats crisscrossing the area. This was difficult to capture nuance, but they did a great job, while albeit being fairly slow. We then tied that to some updated bathymetry near the breach to complete the overall picture, and the breach is to the left side of the screen. This was our main tool of determining where sand was, and it allowed us to confirm our suspicion that there was enough to construct all phases of work. The black line outlines depict where our islands were. These islands were sand that were above the floodwaters and where that we could borrow from. Our access road, however, was all the way to the north where that dashed line is. So getting to it proved you needed a boat to get to it. It was surrounded by water. So we got, during this phase of identifying the existing conditions, we got our first taste of how important it is to have up-to-date geospatial data when our bathymetry post-mobilization discovered a brand new scour hole that had developed after the previous bathymetry shot about a month later. It was just as deep, about 100 feet deep, and right in the middle of our closure berm alignment. You'll notice on the closure berm with the big arrow pointing to the hatched area, you'll notice there's a pronounced jog in the northern section of it, and that's when we realigned it. That I'll discuss later. This was our first contingency plan that we dubbed Go Shallow, Go Fast. This realignment allowed us to achieve our target milestones for closure and actually reduce the quantity of sand needed for closure based on this updated bathymetry. This berm was located outside of the main berm's cross section, but it was incorporated into the seepage berm completed during later phases. This decision was very critical, a very critical hydraulics decision, as we'll discuss in a minute. So now we knew where the sand was, we had to get to it, and there's about 3,000 feet of flooded farm field that separate our closest access to the next spots of dry land. So swamp buggies to the rescue. These are basically excavators with float tracks dragging hydraulic power units and booster pumps, and they were mobilized and started creating our access roads, and then begin pumping our sand deposits from the dredge locations over to the breach. They required a depth of about 2 feet of water to operate, and we kept about a 12-inch buffer from the farm field to ensure we weren't pulling up their precious material. We use this in conjunction with live updates to our Civil 3D model to allow us to prioritize and confirm we could get all that we could and determine when areas were no longer dredgeable based on real-time flood elevations. This production was slow, but we did accomplish about 300 feet of closure berm before contingency plan number 2 had to be enacted. We knew at some point this was going to happen. We had to turn this job into a conventional earthwork job at some point or another. This was either when the water drops after our closure or as floodwaters receded. The up-to-date Civil 3D model allowed us to determine when sands were dredgeable and when they weren't. This allowed us to determine what our window was operating and allowed us to make the decision based on the equipment we had. Larger diameter pumps and booster pumps and pipe were already spoken for a lot of the other repair efforts, so we were really working with what we could get our hands on. But using this predictive flood stage and weather forecast provided by our USACE partners, we were able to make an informed decision to pivot early. And the pivot was pretty much overnight, where the swamp buggies that had pumps mounted to them were swapped over for conventional buckets. And they got to work building roads between the sand islands. And that's really when the real magic happened. We dubbed this next phase Farmer Strong. We derived this name based on the amazing camaraderie and teamwork, and sometimes competition on display when you put to task an army of farmers with flooded fields and hungry tractors. The sand roads were built between the islands ahead of the scraper army, while dozers and box blades with conventional excavators turned the islands into usable borrow mounds. When they were done, there was pretty much only water and a highway next to the next island. With this flexible equipment roster, we managed to make hay when we could and go lean as waters rose or weather rolled in. We kept a typical production of about 16,000 yards per day with 30 to 40 scrapers running. My favorite quote during this phase was over the radio, one tractor operator was requesting to have his tractor bumped up another horsepower so he could pull an extra scraper. So with this going on, we were making tons of progress. Closure was imminent, but we knew we had a challenge ahead of us. As closure progressed, the flood stage continued with the full flow of the Niche and some water flowing backwards up from the Missouri, still trying to come through our breach. And This was said a lot, and I'll say it one more time. Q equals VA, and our area was closing fast. To plan for this, we expected an uptick in velocity, and we utilized the program HECRAS combined with observed conditions to develop a predictive model to determine when the velocities would start to work against us. Our major concerns associated with this increase being the loss of our leading edge, shown in the upper left-hand corner to the bottom of that photo. The slough, the scour of the existing levee, and the deepening of the channel as that velocity increased. If you could play that first video. So there was an attempt. We pictured there 8 D8s and 1 D9 pushing a pile that had been amassed the previous day, late into the evening, working to push the sand out towards the breach, using live updates from these dozers, from the survey equipment mounted to them, and hand readings of the slough face on the leading edge of the sand. We knew, we confirmed what we knew would happen. Our closure progress was beginning to get eaten away by the flow of water. All right, back to the slides. The workaround contingency was already in place. We put our model predictions to task. Using HECRAS, we developed a procedure for closure that not only closed the gap, but armored the opposite bank to keep it from retreating and brought the floor up to decrease the shear forces. The riprap sizes were increased as predicted using the tool so that we would have the correct size rock sourced and ready to be placed on site. We did continue filling with sand with riprap armoring while we were advancing the closure to provide a safe workspace for the tractors, but we switched it so that there was more on the land side protected by the armoring. This is a depiction of that final closure area. In the upper right, we have the actual measured velocities against our predictive velocities to ensure we were on track. We wanted to stay below that dashed line. We had an upper threshold of velocity that we were trying to stay below. We did engage geotechnical modeling because as we advanced to our closure berm, our berm footprint decreased. So we utilized the program Slope W and calibrated against observed performance in the field to avoid any equipment loss because the berm shrunk. I'd love to tell you how it exactly went, but unfortunately I had to demobilize, and Natalie Harkins is going to take over and tell you how it all went. Go ahead, Natalie.
Thanks, Adam. Okay, I'm going to stay on this slide for a minute and speak on the final steps towards closure of a breach. We stayed around 200 feet to closure for a few days to a week before we really can make more progress again. Like Adam was saying, we would survey the edge of our berm with the GPS system before departing the site, which really helped us take a look at where we were in AutoCAD and how far we needed to go. So we would take that survey around 8 p.m. and come back early the next morning to find loss of our sand berm right back to about 200 feet to closure, where that velocity was about 6 to 8 feet per second. So safety was always forefront in our operations, and as the water velocity increased, it would eat away that leading edge of the sand berm. Therefore, we needed to make it wide enough so that the equipment had room to work and a buffer of sand so that the equipment wasn't working at the very edge while the velocity was cutting away that sand. The berm also had to be wide enough so that scrapers could bring in sand to the dozer towards the leading edge and travel right back and get more. So at some point it became difficult to get accurate velocity readings with the meter that we had. The meter eventually maxed out as crews worked during the day to close the breach. And at a point, we were unable to get far enough into the breach water to collect the data by the boat as the water became more and more turbulent. So we decided to work days and nights to keep up gaining on the closure. During the day, the crew would make massive piles of sand needed to keep both the day and the night crews working. So we could play the video. after a little, it became apparent that the strategy wasn't working and we had to retool. First, we tried a series of super sacks provided by the Corps, which are 1 cubic yard bags made out of a geosynthetic. Those were replaced by dozers and a barge-mounted excavator to combat that water velocity that you can see here at the leading edge of the berm. We did end up nearly closing the breach with that method, but we could not add super sacks at a pace in which we could close the berm entirely. As we neared closure each time, we would also open up a larger scour hole on the other side, the side that you see right now, land side of the berm, in which we would have to fill in at a later date. Okay, you can play the next video, please. So it was decided to bring in shot rock to get final A-breach closure. At first, we ordered whatever shot rock was available in the area. Then we became a bit more picky as we neared closure. As you can see, closure was achieved by adding shot rock from a barge-mounted excavator from the south, in conjunction with an excavator mounted on a rock berm from the north. The very final rock placed was about 4 foot in diameter, and this was placed carefully by that excavator shown at the north. Okay. And here are some aerial views of the closure at A-breach. The water rose to about 1.25 feet on the riverside during the final closure, but we were able to predict a value similar to that so that we could raise our berm, our rock berm construction to a certain height. So with the shot rock placement from the south and the large diameter rock placement from the north, we were finally able to close the breach A. But after breach A, resources were focused to closure of B breach, which was about 5 miles south of A breach. You can see the design for B breach was similar to A, with a 500-foot wide sand foundation berm, 300 feet towards the land side and 200 feet towards the riverside, with a 60-foot scour hole in the middle to fill. The borrow area was a bit further away with respect to the distance for the borrow to A breach. Also, wildlife preserve was located in between B breach and the borrow area, and we wanted to keep that intact as much as we possibly could. We went through the same process and compared historic LiDAR survey data to more current data, and we were able to find pockets of available sand to bring in for the foundation construction. While B breach closure had its challenges, it was a little bit easier to close than A breach, as you can imagine, mainly because we weren't fighting the velocity of the adjacent Nishnabotna. We were able to identify a channel from the Missouri River that was feeding into B breach, and we closed it off at the source a little bit upstream of B breach. We constructed a rock revetment at that area and slowed the velocity down to almost 0. Due to those proactive steps, we completed closure at B breach with sand only 3 weeks after A breach was closed. And so in December, the Corps tasked us with closing 5 more outlet breaches, C through G, and we needed to complete repairs and achieve our full design levee height by March of 2020. Those repairs included crest repairs, side slope and ramp repairs brought on by the flooding events of the year prior. So in this slide, you can see G breach had its own set of challenges, mostly due to the weather and freezing conditions. You can see the water iced over here. And G breach alone extended 1,800 feet, including 300 feet of an open water section. So some of the challenges from the outlet breach repairs included major damage to access roads, in which crews had to build up roads for one-way traffic. A night shift was added again in early January, and trucking of sand and cohesive material increased over time to 110 trucks hauling sand and cohesive soils on each shift, each truck transporting about 6 loads per shift, which equated to about 60,000 truck miles a day. And here you can see aerials of Breach Street closure. Despite the weather and trucking challenges, Breach Street was closed on February 10th, and full levee height was achieved on March 2nd of 2020. And now I will turn it back over to Dwight so he can provide a summary and some more closing remarks.
Yeah, thanks, Natalie. I'll say a few words about quality control and safety during the work. As Adam described, the 3D modeling was very helpful in terms of evaluating the amount of sand deposits available on the inland borough areas, as well as to optimize the alignment of the closure breach. And as you can see in this photograph, real-time RTK GPS was utilized to help guide the work and also monitor quality. As you can imagine, the deliverables that were required had to be fast-tracked, and the approval process for those deliverables was monitored closely by a submittal register, updated frequently. Due to the size of the levee system, the work areas were often separated by many miles, so we had separate crews managed by our site superintendents, safety and QC personnel. We had individual safety briefings that were held at each location to discuss hazards for those locations. Given the wide area, some of the challenges from a safety standpoint were fatigue management, communication, and congested work areas. As mitigations for those, we employed rotation of operators so that they kind of minimize burnout. We used CB radios in both lead equipment as well as to communicate with all the truckers to be able to convey real-time road conditions and other information, and to basically try to help coordinate the work between the various areas. During the safety meetings, we encouraged workers to voice any concerns that they had, to get in as much engagement as possible. And we also implemented during the work a gift card safety incentive program to help encourage safety suggestions, as well as to reward best practices. Those were given out, on the spot and or presented at the following day's safety briefing, just to reinforce again the importance of safety. Team collaboration was key. I think one of the real successes of the project was the dedication and can-do attitude of everyone involved. Everyone from the operators to the supervisors to the Corps of Engineer personnel, and also the support we got from our stakeholders, other stakeholders. It was really a team effort. It was done under a contract through the Omaha Flood Recovery Office that was streamlined and provided flexibility for us to be able to adjust quickly and as needed to address changing conditions and or to pivot when necessary to address other changing priorities. A key component of the work was the project delivery team. Again, this was led by members of the Omaha District Corps of Engineers, and was also included with representatives from Weston, our subcontractors, and other key stakeholders. The PDT was, I think, very instrumental in providing a forum for open and early and often communication. And we met at a minimum weekly and often more frequently to keep everyone informed of the progress, any challenges and workarounds that were needed so that those decisions could be made on a rapid and real-time basis. So to summarize some of the takeaways, I think, from our experience, I've listed on this slide. Again, the contracting mechanism was tailored for a fast-paced emergency response for infrastructure repair as was necessary in this levee repair in order to help us achieve objectives and get those completed within an accelerated time frame. And again, through the framework of the project delivery team, that was essential. We leveraged local resources and equipment, I think, to a very high degree. This allowed for a lot of the money to flow back into communities affected by the floods. As both Adam and Natalie indicated, contingency planning and being proactive were I think integral to completing the mission within the time frame that we did. The technologies that were described were useful and to optimize the completion of the work. And then lastly, again, to foster a safe work environment, we empowered the workers to be a part of that mission, as well as reinforced best practices with a safety reward program. So with that, Daniel, I'll turn it back to you for any questions or comments.
All right. Thanks, Dwight. And thank you, Adam and Natalie, as well, for the great presentation here. So I just wanted to let everybody know we're going to start the Q&A session now. So if you've got questions for our presenters, go ahead and put those in the Q&A tab there at the top of the chat pane. If you see a questions in there that you like or you want answered, hit the thumbs up next to it. That will help it rise through some of the other questions and rise to the top so we can get to the most pertinent ones for presenters here. And you can also go ahead and grab PDH certificates and the slide deck, if you like, from the handout section as well. So let's go ahead and get into some Q&A here. So I think the first question that I had for all of you would be, I know in the original article, you talked about the impact that the project had on the local community and how you really leveraged the resources of the local farming community to help out. So just kind of what was the reaction to that, and expand a little bit more about how it really kind of contributed to building the community resilience with it.
Well, this is Dwight. I'll take a stab at that one. I think it was really critical. A lot of the operators and some of the laborers that were involved in the work on the crews were, from families that were directly impacted by the floods. So they had, skin in the game, and they were quite motivated to be part of the solution. I think also because a lot of these farmers were put out of business by the flooding, they did have equipment that was available that was needed for, moving these large quantities of materials from the borrow areas to where, they were needed. So I think, it was a win-win in that regard. And also the contracting mechanism allowed us to kind of use equipment and resources on a somewhat a la carte basis so that we could turn resources on and off as needed. and that allowed for very rapid pivoting. It was not unusual on the way home in the evening to see these large scrapers, moving down country roads to the site, because mobilization was basically, hook up your scraper and head down the road. So those were very cool, I think, to see that kind of response from the local community, and I think they were very appreciative of being part of the solution.
Great. Adam, Natalie, anything you want to add to that?
Reiterate, but to come out of the flood with the community, it affected us as much as it affected them as far as getting around and finding resources and learning the tips of how to get around. The community was there to really assist us in that, and that was really nice to be a part of as well.
All right, great. So here's a question maybe for Natalie here, since I think you were talking about for the B breach here, about abating the flow of water upstream was so beneficial for that closure. Is that a technique that is used often whenever there's a breach?
I think it could be depending on location, definitely. For a breach, we couldn't do that because of the geography in the area. We were right on the bend of the Nishnabotna River there. But B breach, we were able to find a little inlet and close that off with shot rock before we closed B breach.
All right, great. So here's another question from Matt Hoy about the initial closure for A breach. What methodology was used to size the riprap placed within the breach during the closure? Did you use, did this sizing prove appropriate based on observations, or was a factor of safety needed to keep the riprap from mobilizing?
I could take that one if that works all right. The predictive models, what's the one, the Holstrom curve, and that's covered in that. There's an engineering manual that discusses predictive modeling of erosion. There's such a large quantity being dealt with that it was we weren't measuring exactly to be able to run it back to it, but we did look at those models and basically double was kind of the rule of thumb on sizing, where when you start seeing 3-foot diameter riprap move in water, it's humbling for sure, and that was something that we did see there close to the end. But as far as where we expected to start to lose ground, it matched pretty well with those predictive models. Good question.
All right, so here's another question about kind of, I'm going to combine two of them since I think it kind of covers some of the similar territory here about kind of what the daily battle rhythm was like. And I believe you talked a little bit about having, day crews and night crews working on this, but, what was sort of like the daily rhythm on that, and how did status updates get communicated to your stakeholders, local, state, USACE, and so on from there?
Well, this is Dwight. Well, when we pivoted from the hydraulic mining to mechanical mining of the sand, we, in order to keep up with the demand, we had our swamp buggies. We had 5 swamp buggies, and they were excavating both night and day shift. So the purpose or the objective for the night crew was to mine and stockpile as much sand as possible to get some draining of the sand, so that during the daytime, that sand could be transported to the breach. At the beginning, at least, we transported the sand during the day. We mined both day and night, and that seemed to work pretty well. Basically, the transition from the night crew to the day crew, they would provide an update of the estimated volume that they excavated and from what locations. It was somewhat humorous that each of those kind of islands that were kind of popping out of the water a little bit, as Adam showed on one of his slides, had different geographic features. So, they were called, I think one island was called Cuba, the other was Iraq. And so we would get updates in the morning as to, where the material was mined and available at Cuba or Iraq. And that allowed our daytime crews to be able to determine the cycle times that were needed to retrieve that sand. And of course, we were somewhat opportunistic where we tried to get some low-hanging fruit early on. But as the work progressed, of course, we had to move further away from the breach to obtain the sand. So it was definitely all hands on deck exercise and battle rhythm. That's a good terminology, because it was a battle, and everybody was focused on the mission.
All right, thanks, Dwight. So I've got another question here. This was two people have asked this here, Ron and Jason, about how the members of the community and the farmers that you kind of leveraged here, how they were compensated for their time and equipment. How did you manage that interaction?
Contractually, we worked through a local subcontractor who was based in Hamburg, Iowa, which is nearby. And the subcontractor had already recruited and signed up dozens of personnel even before we mobilized. They were very proactive, saw that there was going to be a need for a large number of tractor-pulled scrapers and excavators, dozers, which they knew, were available in the community, the farming communities. And so they did a great job of signing folks up, getting them, making sure that their, safety documentation was up to date, getting them entered into their system so that the prevailing wages were paid correctly. So a lot of that was really done for us before we even mobilized, which of course was one of the benefits of selecting that particular subcontractor, is that we were impressed by the amount of effort that they had already put into organizing that work. And then every day we had, sign-ins for each individual, which was basically an operated rate. So we were able to track who was on site, what type of equipment they were using, because different equipment had different rates. And that was how we were tracking that on a daily basis. We did have an on-site cost tracker that was taking or tracking the incurred cost, so that we knew from day to day without any delay what our incurred costs were. So that we weren't waiting, weeks for an invoice to show up. We already knew what costs were incurred, and then when invoices were received, then we were able to cross-check those invoices with the daily sign-ins and verify, that they matched up, and sometimes there were mistakes and corrections were made. So that system worked, quite well.
All right, great. Thanks, Dwight. So another question here, I saw Karen just put in here about what type of contract acquisitions we utilized for the project.
Again, we used a unit priced approach for most of our work. We did some fixed price work, but for the most part, due to the dynamic and fluid nature of the work, we used unit prices again for operated equipment. And that way we were able to, again, kind of use an a la carte approach to decide, turning on and off resources depending on the need.
All right, thanks. Let's see. I think we've got, we've got a little bit more time for some more questions. So if you've got more questions, feel free to keep putting them in Q&A here. So here's a question from Terry about the levee itself. He says, when was the levee built? I think the levees, it would have been built for the floods in 1993. It was built after that. Was the 2019 flood worse than the 93 flood?
I believe that the levees were actually constructed in the late 40s, early 50s, if I remember correctly. If there's anyone on from the Omaha district, they would know for sure. I do recall that the river levels from this 2019 event were record levels in terms of the staff gauges at the Brownville, Nebraska location. They were the highest on record. So they must have, I'm sure 1993 was a bad one, but I believe the levels in 2019 were the record.
All right, and here's a question that I saw David Harris just put in here. He said, are levees designed with homogeneous cross sections and riprap, or is there any zoning and/or tor drains?
Yes, Adam, I could take this one. Different levees are designed for different purposes. These don't have a static head behind them. They're there to protect when the waters rise. Some sections had seepage berms associated with them of various distances. Some of them had drains, dewatering wells associated with them to help keep groundwater down. But these were all sand, just homogeneous berms, and some sections had an armoring on the riverside to prevent against scour.
I guess it's probably worthwhile to note that the sand or the core of the levees were non-cohesive, generally sand, and then 5 feet on riverside and 3 feet of cohesive on the land side. And you mentioned relief wells, Adam, and yeah, there were 232 relief wells within this levee segment, L550. And all of those were inspected and pump tested, and in some cases refurbished and or replaced as part of the scope, which I think I failed to put on any of the slides, but that was also a fairly significant effort as well.
All right, and I got another question about your work with the local farmers here. Jason, I'm going to combine kind of your two questions together since I think they cover some of the same territory here. So for the local farmers, do you know if they continue to work for the subcontractor afterwards, or is there any plan to keep them, kind of on tap for a quicker response to future breaches? And as kind of a follow-up to that, do you think it would be advantageous, or is the current model of labor more conducive?
Well, we actually, to this day, continue to do some follow-up work at L550, doing some kind of punch list things. And we continue to go through our subcontractors, so they work directly for the subcontractor rather than Weston. And we have a much smaller workforce now. I think given the experience for this response, that it would be, easier to replicate for any follow-up, but there really isn't any current plans or funding for, a kind of rapid deployment force of, if you want to call it that, it would have to be kind of restarted if this situation or a similar one occurred in the future. Not sure if that answered your question, but that's kind of the current status, at least, is that there's no plans to have anyone on tap, so to speak.
All right, great, thanks. So I think that looks like about it for our Q&A here. So I think I'm gonna wrap it up here if nobody else has any other questions. So I wanted to thank you, Dwight and Adam and Natalie, for your presentation and for answering our questions here. And thank you to all of our listeners out there for attending the presentation today. If you're interested in submitting an article to the military engineer, you can visit our website and check out our editorial calendar with our upcoming themes and our guidelines for writers. We're currently open to articles for our May-June issue, which is going to focus on project delivery, and proposals for our July-August issue, which is going to focus on water planning and management again. So before you head out, make sure that you download your PDH certificate from the handout section here. And you can also find the slide deck, of course, if you want to download that and look at any of the maps or other content that was provided today in a little bit more detail. So on behalf of SAME, the military engineer, and our featured presenters here, thank you all for joining us today. Have a great rest of your day, everyone.
Thank you.